class. So we have a few objectives. We did cover several in last class. For example, we demonstrated a few examples of extruded products like snacks, like texturized meat. So those things. But today we'll be focusing more about the fundamental part and also how to precisely control the system, as well as when we get the product is not feasible, how we adjust the parameters to kind of finely tune the system. Okay, so we started with the talking about two types of extruder. I guess you guys are very familiar with a twin screw extruder and a single screw extruder, right? We briefly mentioned last week. And also we will mainly focus on all the chemical and physical changes that will occur during extrusion, and also how the food components, they interact with each other in the extruder. Okay, and finally, what can we control basically to adjust the product properties. So I hope that this class can help you to learn more practical and also fundamental knowledge about extrusion. So first, because the extruder is not like a dryer or a lot of other unit of operation that you guys probably can imagine in the daily life, but extruder is more sophisticated or complicated equipment that most of you probably you guys have seen how it run, but really it's hard to imagine what is inside there. So I will warm up with watching a video. Okay, so probably let's get a little bit more familiar with this equipment. So let me change my share. Okay, share screen. Okay. Okay, let me stop here. So I hope that you guys now you can look into the inside and see really how it works, right? So basically they are feeding. Let me see if I have an image. Oh no. Okay, so I don't have an image here. So probably you can see that there's feeding, right? At the very beginning, and then there's a screw that is pumping all the material forward. And then in the middle, you have a water intake, right? And then finally, there's another potential feeding tank. So that one is not necessarily there, but at least for most extruder, there's one feed tank and one water feed. Okay, and then during the pumping process, you see the particles gradually gets melted because their temperature and pressure builds up gradually. And you can also see there are several bending portion on the screw to release some pressure during the process. Otherwise, the pressure will be built too high. So that's most of the extruder looks like, okay? And it's very versatile. I showed you this table before. It can be used to produce a lot of puffed snacks, for example, Cheetos and the cereals, which will be making this Friday. It's quite magic because you'll see that you feed those whole grains or cornmeals, and they came out with those snacks in just few seconds. Okay, and also can be used to make pastas and also a lot of other texturized proteins. So it's very versatile depending on how you control it, right? So here you can control the screw speed, feed moisture, and product temperature. Okay. So here, this is a photo that we took from our extruder. Okay, so you can see that here's the equipment. Okay, so if you look at this flow chart, this is like a diagram. You can see that there's a feed tank, right? Feed tank with a parameter you can control, which is a kilogram per hour. That's the feed rate. Okay, let me see if I can mark it. Pen. Okay, so this is a feed tank. And here you'll see is the water feed basically. Okay, so here you have the water. So probably you can take some note because I actually have another simplified chart in later. And here the water and the feed will be mixed in the early stage of the mixing of the screw. And here the screw part, you can see the screw has actually 10 zones. Basically from 1 to 10, actually it will pass through all those zones. Okay, and the zone, because our extruder is one of the advanced version, it's quite expensive, but you can control basically, you can set the barrel temperature at all 10 zones. Okay, so for zone 1, we can set it 20, and the actual might be 10, 0, and it'll be changing. Oh, actually, you set the bottom. This is where you set temperature, and the yellow one is the actual measured temperature. So they don't necessarily match well, it will try to, when it stabilizes, it will try to approach your set value. And then here you'll see there's a bar, which is the pressure, okay? And also you see there's a amp. Amp is the how much is the current, okay? So the larger current, the more power it is running. And the RPM here is the screw speed of the motor, okay? And here you'll see a torque. So torque means you can see the unit is in percentage. So because the torque is means how much power or how much resistance that the screw is currently facing. For example, if we are in 100% of torque, means if there's more friction that is needed generated, then probably our equipment will be jammed because the screw just have so much of power to rotate, right? Because you can see that in the feeding part, we have to kind of crash every particle into melted version. So that requires a tremendous amount of force to rotate that screw. Okay, so torque is usually shown in percentage. Okay. And then here you'll see there's a SME, which I will focus a lot today to discuss what is SME. So this is a specific mechanical energy. Okay, so based on this diagram, what do you think we can control in this system? Can we control the feed rate? Yes, right? So we can control the feed rate. Can we control the water feed rate? We can, right? How about the screw speed? Can we control the screw speed? Yes, right? Then can we control the pressure? Is pressure something we can control? Actually, for pressure, we cannot set it to a certain value because it's one of the passive parameter. It's kind of the reflection of the current processing conditions, but we cannot directly set the pressure to a certain value. Okay, can we control the barrel temperature? We can control barrel temperature, right? Because that's all the value we can set. So probably you can see that there are some values we can directly set it to a certain value, but for some parameters, they are like passive parameters. We cannot basically directly use the control panel to turn them to a certain value, right? So here's the very important part of the extrusion controlling system. So as you can see, the extruder is such a complex system that we can only control a few parameters, and then as many of them we cannot set them to a certain value. So typically in a lot of research and their previous work, we tend to treat the extruder system as a black box, which means we can change what we are trying to feed into it, but we really cannot do not know what is coming out, or it's hard to predict. And there are a lot of factors they kind of counteracting with each other. So there's several ways if you want to change one property, there's several ways you can adjust the parameters. And also, on the other hand, it's also very delicate, um, which is the one of the biggest issue with the extruder. I don't know if you guys heard about is the clogging. It's a jamming problem. So actually, we were doing a test running last week. Molly had a terrible jamming issue um, after the process is over when she was trying to shut down, and it really took her about 1 day to to fix that issue and be able to put to disassemble the system, because you can see that there's screw, there's a die. So every time after we run the system, we have to disassemble and take everything apart and to wash it. And then so that actually, if it's jammed inside, it really takes forever, because you can imagine those starch once it's burned, then it's quite stiff and it can bind everything together. Okay, so here you can see we have a lot of parameters in the in a extruder, right? So typically we classify those parameters into process factors, which are those processing conditions that we can directly control. And there's a system parameter. So for the system parameter, basically it's something that reflects how the system is running or how much energy we are giving, but it's something that we cannot directly control. And finally, we will have the product properties. So it's like so that's why it's like the black box. In the black box, in the input section, we have all the process factors, and then in the output section, we have all the product properties. Okay, so here I'm going to focus on the specific mechanical energy as the system parameter, because that's the one that is the most important in a lot of extruders. Okay, and we'll talk about how can we use those processing factors to control the specific mechanical energy. Okay. All right, so first I want to give you a brief definition about this terminology, the specific mechanical energy. Usually we call it SME. So SME is a measure of the how much mechanical energy went to the composite system. Okay, so for example, if we are processing starch, starch-based snacks, then the SME will be telling us how much um, heat or how much energy has the starch been absorbed in order to be cooked, right? Because when we did something microwave last week, right? You know that water takes such amount of energy to get boiled, right? So for starch, it also takes certain amount of energy to get them into gelatinization and sometimes browning effect. So that's why it's quite important for us to monitor it. Okay. Also, this energy can influence the melting and also the interaction between other components. For example, the protein and starch can form a complex during the extrusion, right? That's what we call the type 5 resistant starch, right? So that there are a lot of those uh, 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 properties that we can control using this parameter. Okay, so here I want to show you the equation about the SEME calculation. Okay, so the SME is equal to on the top we have the motor power. P is the motor power, and the gamma, the torque. Okay, the torque is the actually you can see that's the percentage of the resistance that our extruder is trying to overcome, right? So the maximum is 100%, right? So the torque will be in the unit of percentage, and we have the ratio between the RPM actual versus the RPM rated. So RPM actual is the actual screw speed that we're using, and the rated RPM is the system default RPM actually. Okay, and in the bottom we have the mass flow rate. Basically, it's our feeding rate. And after we put all the unit in, and after cancel all the unit, the output of the specific mechanical energy will be kilojoule per kilogram. So as we mentioned that's the unit energy that is absorbed by unit mass of the material, right? So there's an alternative way to calculate SME. Okay, so the torque we can use so that's the way that how we measure the SME, because in our system it's very nice system and it automatically calculates the SME for us. But in the 90% of the extruder, we have to manually calculate SLE, and typically we have to follow this equation, which is in our alternative, because it's more um, uh, sometimes it's more practical for using, and we also practice use this alternative SME calculation. But theoretically, you'll get the same value regardless of which equation you use. Okay, so here you see that we have the torque minus the torque at no load, okay, and divide by 100%. So that's the comparison um, between the loaded torque and the no load torque. Basically, how much the percentage of power that we're using of the system. Okay, and the second terminology is the same. We have the screw speed and we have the rated screw speed. Okay, And the PR is the rate power mode power. Basically, it's the overall power that we are supplying. And for the mass flow rate, we'll be using kilogram per second. So very similar. So let's do a quick practice. I'll give you about 3 minutes. Let's calculate the specific mechanical energy, and we'll solve this together after 3 minutes. Okay. You guys ready? All right, let's solve this together. Okay, so I think I forgot to mention one thing that when you plug in the let me see. Oh, okay. So when you plug in the torque in percentage, let's use the 40 instead of 0.4. So here, when you see this number, it's already in percentage of unit. So you can just put it 40 instead of, divide by another 100 because we already divided 100 here. So let's solve this together. So let's plug in numbers. So at the top, we have 40, right? Minus 7 divided by 100, right? So that's the torque percentage, right? And times. So I encourage you to leave all the units here because because our SME is the very specific about the unit. It's kilojoule per kilogram. So in case that you kind of get lost for all the or the unit just to keep them and then try to cancel them during the calculation. Okay, so then we plug in n number is 300, right, which is measured screw speed. So 300 RPM. And then bottom we have 500 RPM. Okay. And then we plug in our power. So our rated power is 20 kilowatts, right? 20 kilowatts. And on the bottom, we have the mass flow rate, right? So which is 0.02 kilogram per second. Okay. So now first we do is to cancel all the units. For example, RPM can be canceled. And what we get, okay. So what did you guys get? Can I give you a number?
I got 198.
Okay, thank you, Abby.
I got the same.
Okay, thank you. So 198. Okay. So on the top, we still have kilowatts, right? Kilowatts. And in bottom, we still have the kilogram per second. Right. So right now we know that because for physics, we know that watts is equal to, so watts is equal to joule per second, right? So here, if we replace the kilowatt by kilojoule per second, then we can actually cancel the seconds, right? So let's place it equal to the, on the top we have 198 kilojoule per second. Right? So now you can see that our seconds can be canceled, right? And the final unit is 198 kilojoule per kilogram, right? So that is how much energy is absorbed by 1 kilogram of our product. Okay. Does that make sense, guys? Okay, I think that's a very simple calculation, but the unit is the one of the most tricky part, because a lot of case, for example, when we are measuring our flow rate, there's no way that we measure the flow rate by second. Typically, it's by minute. Okay, so that's one thing, and also sometimes for the motor power, it's given by watts, not kilowatts. Okay, so in that way, we have to, kind of change the unit correctly. All right, so we have talked a lot about the SME, the calculation, the definition. So so my question is, how can we control the SME using those factors? For example, for screw configuration, which screw for example, the twin screw and the single screw, which one has better, larger SME? For example, the die geometry, do we want a larger die to increase the SME or smaller die? And for the feed rate, the larger feed rate. So basically, I'm trying to let you guys discuss how to control those parameters in order to finely tune our SME value. Okay, so I'm going to put you guys into 7 groups. So each of your group will be discussing one of the parameters here. Okay. So after maybe 5 minutes, we will come out here and to share our answer. And I'll assign the groups automatically. Okay. options, time, maybe 4 minutes. Okay. Okay, now we have everyone back here. So we got some tricky groups, and some groups might have very straightforward answers. Okay, so let's start with group one. We have Chloe, Harmony, Misha, and Veronica. So what do you guys think about how? So for screw configuration, for example, single screw and a twin screw, which one will generate a larger specific mechanical energy?
We were saying that probably the double screw would contribute to higher torque, leading to a higher SME value.
Yes, that's correct. So majority of cases, the twin screw extruder is definitely more powerful than the single screw extruder. Okay, and also it creates a little bit more of the friction, and all the reaction inside will be a little bit more intense. All right, good job. For group two, how about the die geometry? This is probably one of the trickiest. Let me see. Oh, probably one of the trickiest one. Okay, so we have the Arm, Emma, Yvonne, and the Sophia.
We figured that with a larger die geometry, we would have a lower SME value because we figured that with smaller smaller holes and stuff in the die, you'd probably need a greater motor power, which would affect the equation.
Good job, good job. Yes, so smaller die, you get more resistance to push everything out, right? Yes, yeah, that's a very good answer actually. So we can, if we have larger die, then everything will move smoothly. But if we have a small die, then all the pressure, temperature will build up crazily inside that system. Okay, good job, group two. So for group three, you guys will be talking about the feeder rate. Okay, so this is also one of the tricky one. Okay, all right. So group three, we have Jackson, Kristen, Madison, and Zoe.
We just
we
kind of
said
thought. Oh, you go
Oh,
ahead.
go ahead.
we said that the increase in feed rate would decrease the SME, just looking at the equation and having the mass flow rate on the denominator of the equation.
Yes, that's right, Jackson. That's from the equation to think about it, it's absolutely correct. But but my question is, because I call it tricky because it's kind of has double blade effect. So when we increase feed rate, do you think the torque will change? Do you think the system will have a greater resistance to operate?
I'm not sure.
Yes, so think about when you have very small amount of feeding, then probably you won't have any resistance, right? Just like when we almost in empty running, then the torque is, at the base level, which we just used 7%. But when we gradually add the feeding, then the torque percentage will gradually build up, right? So if you look at the equation before, So we have the torque percentage on the top and the mass flow rate on the bottom, right? And then when we increase the mass flow rate, we are increasing both the torque usage and the mass flow rate. So it's kind of, we're increasing double both sides. So it's very, sometimes in majority of case, as you said, we'll see a slightly decrease of the SME, but a lot of case, the SME will maintain in a relatively constant value range. Does that make sense, guys? Yeah, that's because we're inducing both effects on cell. That's why the Extruder is such a complicated system, because every parameter you change is not one dimensional. Sometimes the effect it brings in is multi-dimensional. Okay, but good job, guys. I think the way that you guys have interpreted it was pretty good enough. Okay, so for group 4, you talk about the moisture input. Okay, so how much moisture feed will impact the SME. So we have Jared, Miley, and Michaela.
We said that more moisture would decrease SME because,
why is that?
Well, it would affect the mass flow rate at the bottom and it would make the denominator bigger, but it would also decrease viscosity, which would decrease torque.
Exactly. That's the very good answer. Actually, you answer both sides. First, it will change the mass flow rate to be larger. Second, it will decrease torque. So yes, so moisture input is one of the most significant way that we can monitor, or we can modulate the mechanical energy input. Okay, good job, group 4. And group 5, how about if we induce a secondary feed like what we have seen in the video? How does that impact the SME? So we have Carly, Emmy, and Justin.
We were kind of talking about, I mean, we thought it could kind of go either way because it depends what you put in. But we were talking about if you were putting in more of a like liquid or moisture input, then that would slow it down. But then if you put in something that would help speed up the mass flow rate, like we didn't know exactly what kind of feed was going in, so we were like, it could go either way.
Good job. Yes. So it really depends on what you put in. Yes. If you are just adding water, then we'll, like group 4 just said, will decrease our SME quite a bit, right? But if we're adding something very dry, then probably will increase the, will serve very similar to increasing the feed rate, right? So it's very hard to say depending on what we are putting there. Good job, guys. That's a very good, good answer. Okay, so for group 6, screw speed, how would that impact the SME? So we have, oh, we only have Chris in the group 6.
It's actually me and Lauren, but no worries.
Okay.
I can just say what we were discussing. We just said like if the screw speed was higher, so if the whole thing was faster, then that would mean more mechanical energy. And then looking back at the equation, we also based our answer off of this because the ratio of what was it? The screw speed, since it's in the numerator, overall, if it's a faster, then it'll be a higher SME. And then
good job.
Vice versa.
Yes, that's a very, very good answer. And screw speed, the impact is usually one direction, right? So if we increase screw speed, typically it will drastically increase the energy that you input there. Okay. All right, so for group 7, our last group, you guys will be talking about the barrel temperature. So we have Abby, Kimiko, and Paris.
Yeah, so we talked about the temperature and we thought it might increase the pressure with an increased temperature. and that will obviously affect your SME. And then we also talked about how it could affect the viscosity of the fluid or the product because temperature and viscosity. But yeah, so it could increase it or increase your SME overall.
Right. So so this one is also very tricky because it's no one direction of the change. It really depends on the material you are operating and what temperature you are trying to achieve, right? So I think Abby, your group answered very well because depending on the viscosity of the material processing and how much temperature you want to adjust. For example, if we change the temperature to a burning temperature, probably everything will be jammed. It will require a lot of will cause a lot of viscosity, right? But in some case, if our barrel temperature is very low, then probably there's no phase transition happened in our material, then we'll probably have very small or large resistance depending on our original feeding material, right? So there's no answer, like no direct answer to this question. Okay, so good job, guys. I think that's a very good discussion. Okay, so it seems you guys have a very good understanding about the SME right now. So here I'm just showing you one of the example that was back to 10 years ago when I was working on extruder. And here's a set of data that I collected using the feeding moisture content to control the SME. So for a different sample, you can see it's almost linear correlation between the how much moisture content and SME. And you can see it's very, very sensitive because the way that we adjusted is really just from 10% to 14%. Okay, so the feeding moisture window is a very small window, but our SME changed quite a bit, right? So it's a very, very sensitive way to modulate the specific mechanical energy. Okay. All right. So we talk about a lot about the how to calculate, how to control it. So here's the reason why it's important. For example, we learned that a lot of plant-based meat, they're produced by the extrusion, right? So basically, they're texturized proteins. And for principle, the reason that we can make the protein to be fibrous is that we are creating a disulfide bond between those peptides. Okay, so on the left side, you will see there, this is the native globular protein. For example, can be soy protein, pea protein, chickpea protein. A lot of plant proteins, especially storage proteins in seeds, they are globular in terms of their morphology. And when we add a lot of water there to hydrate it and apply some shear, they will actually be unfolded. That's what we usually call as a denaturation. Okay, so in this case, in the extruder, the protein will go through the denaturation, but it's more like a guided denaturation. We want it to denature in a certain way that we have planned. Okay. All right, so once the protein is denatured, it kind of lost all the original conformation. For example, it was globular. You can see all the proteins, they kind of wrinkle, they kind of fold to each other. And but once it's unfolded, it becomes like a very long chain structures. Okay, so you don't see any of those folding. So you lose a lot of those beta sheet and alpha helix structures. Okay, and then when we after unfolding, when we apply a lot of shearing, we are kind of rebuilding those 3D dimensional structure by creating the disulfide bond. Especially after die-cooling, you see a lot of cross-linking be found between those peptides. Okay, and then by creating the degree of the cross-linking, we can actually control the degree of texturization or the texture. Okay, so the way that we control how much cross-linking that we want to achieve, basically we'll use the specific mechanical energy. Okay, so any questions about the protein texturization process? Okay, so here is the most recent study that they have done to use the SME to control the tensile strength. So tensile strength basically is how much you can pull it and it won't break. Okay, so in meat we know it's very tensile, right? Sometimes we cannot, during our chewing we cannot even break it. So you can see in this texture-like protein soy, the more SME we put, the larger tensile strength it will achieve, right? Basically, we're inducing some sort of the cross-linking, right? So that's the way that we apply SME to control system, control the product properties. Okay? And here's the chewiness. Okay, chewiness is another property, basically how much time do you have to chew to break it. So there's in a texture analysis, there's several terminology in the TPA analysis. So chewiness is basically a repeated pressure test. Basically, for example, the first press, we can achieve a certain amount of force to break the structure, right? And then chewiness is how repetitive that is. For example, after several pressing, it still keeps some elasticity. Then probably we defer that kind of property to chewiness. Okay, and for hardness, it's just a one-time pressing test. Okay. So in meat, we know another effect of meat is that it's very chewy, right? Compared to a lot of soy protein like tofu, it's very just if it's if it's broken, and then it's no longer holding that strength. But for meat, typically the retention of the mechanical strength can be maintained after several times of the pressing. Okay. So this is the SDS page. If you guys don't never heard about it, that's okay. So basically, it's a very simple way of the chromatography. Okay, basically, you guys probably learned from the orgo, the one level organic chemistry or the genetic chemistry. There's a chromatography, right? So the larger molecules, they will run a little bit faster, and then small molecules. So in this specific paper is that the larger molecule run faster than small molecules. Okay, so everything will start at the bottom. Okay, and then there's a electric field that we apply to kind of move that molecules to the other direction. And then the higher it reaches, and then the larger molecule that is. Okay, so we have actually those standard showing the at different distance. Okay, so for example, here 10 means 10 kilodalton bar. Okay, and at the top you see 170. That's 170 kilodalton bar. And so this is marker. Marker is the standard that we run. Every time we need to run a marker to kind of to calibrate the SDS page. And then, and here you see SPI 1, 2, 3, 4, 5. Those are the different samples we are trying to test here. Okay, so SPI is the native protein, and you can see that it has a lot of molecular weight around here, which is about 20.83 kilodalton. And there are some aggregates, right? Probably around 90 something. You have a bar, very dense bar, showing there's a lot of protein in this sites. Okay, and you see a lot of in the 84.13. Okay, and some in 62.21. Okay, and those all represent different degree of aggregations. All right, and 1, 2, 3, 4, 5 are our textualized samples. And here, if you look at here, they're made by different SMEs. So the larger numbers represents the larger SME it has received. So you see that after the fusion process, more protein are aggregated because if you look at let me see if we can mark it. So for the native one, you see barely nothing at high aggregates level, okay? And for those 1, 2, 3, 4, 5, you see a lot of proteins. They're quite a lot of those large aggregates. But we cannot quite differentiate what's the difference between 1, 2, 3, 4, 5 because it's very minor difference. Okay, probably we have to use more advanced technology to see, to compare how different SME equals to different molecular size after processing. But basically the main difference that the cross-linking between those proteins to kind of link to each other to form those 3D network, all right? So any questions about understanding this part? I know this it could be very unfamiliar to understand, right? Okay, good. So based on what we have learned, let me ask you a question. If we are processing a plant-based chicken, but the protein does not hold together very well, for example, it's too crumbly, and once we chew it, it just fall apart. How can we adjust those parameters to improve the texture? Can we increase the screw speed? Yes, right. Because when we link back to our SME, we know that the screw speed can increase the energy input, right? So the more energy input, the more cross-linking we can generate. And then can we increase additional water supply?
Wouldn't we want to decrease the additional water supply?
Yes, exactly, Warren. So when we want to, if we are feeding water, then probably we have to remove that water supply or decrease a little bit, right? So if we are not feeding, probably we have to dry our feeding material a little bit more so that the initial moisture content can be lower, right? Good job. So how about die diameter?
Would we decrease that as well?
Yes, we'll decrease the die diameter, right? So if that helps, exactly. How about the barrel temperature? Well, barrel temperature can be a little bit tricky, right? Because it does not necessarily directly link to the energy input per unit volume, right? But that's the mechanical energy. If based on our monitoring system, if we see our temperature is not reaching a certain level, probably we can add additional temperature, right? By heating the barrel. So probably barrel temperature can be a little bit higher, but that's not contributing to the mechanical energy, but it will contribute to the overall energy input, okay? And the feeder rate. So feeder rate, feeder rate is, we know it's quite tricky, right? It has some double bladed impact. If we reduce the feeder rate, probably we're also reducing the torque. So not necessarily that will increase the SME, right? So the most common parameter that will change in this process if we want to make the tenderness or the chewiness of the meat a little bit better is that we'll probably increase the screw speed. reduce the water supply, or reduce the die diameter. Okay. Okay, that's a good job. All right, so how about the glass transition, glass gelatinization? So we know that, so in our Friday's lab, we'll basically cook the raw cornmeal directly into those puffed snacks, okay? So in this process, we're actually triggering the starch gelatinization process, okay? And actually the degree of starch gelatinization is also proportional to the specific mechanical energy, okay? So the more power input, the more starch will be converted to a gelatinized version. All right. So this was another work that we done before. Basically, we were using the SME to control the digestive rate of the starch. So basically, I'm not sure if you guys heard about the glycemic index before. Have you guys learned about this before? No. Yeah, sort of, right? So glycemic index means how fast the starch is converted to sugar in your body. So, for example, a lot of diabetes patients, they cannot eat fast digested foods. For example, white bread, they have to probably go with those fiber rich bread or something related to resistant bread. That's because when we have the blood sugar boosted due to the fast release of the sucrose, fast release of glucose, then our body will be responding by producing a lot of insulin. So which is periodically it's not feasible to our health and will potentially lead to type 2 diabetes. So the food industry has been trying very hard to produce slowly digestible starch. So the starch, instead of release everything in a peak, we want a more sustained release of the starch. Okay, so this way is more preferred. Okay, so in that way, we want to create a more slowly digestible starch. Okay, so but in a food, starch-based food, we only have this certain amount of starch, right? When we increase the slowly digestible starch, we will be reducing the rapidly digestible starch. Okay, so this is a chart that we collected 10 years ago to see how the SME is impacting the amount of starch that is fast released and slowly released. All right, so it probably can see that the rapid release starch increases with the SME input, right? And the SDS, slowly digestible starch, can be high amount of those slow starch can be achieved at low energy input level. Okay, so gives us another way to produce the foods with different glycemic index, right? And you can see it can be tuned in a very precise way, right? So here, for example, if we want a certain, for example, half and half starch distribution, probably you can go with the SME somewhere greater than 400. Okay, so this is another way of applying the SME in controlling food properties. Okay, so here's the table of the high glycemic index foods and the low glycemic index foods. So for example, the white bread is probably not good for our human health because it releases all the starch very quickly. Okay, but if we have high fiber, then we can slowly release those glucose. Okay? And high protein products is also highly preferred. All right, so here's our last discussion before we finish. So we have talked about so many processing parameters that we can control during a extrusion system. We talked about screw speed, torque, and also other parameters. So, but why do we specifically use this terminology to control our system? Why can we say, okay, if you set the screw speed at certain value and torque at certain value, then you can probably produce the food product with a certain properties. But instead, why do we want to use convert to another parameter instead of directly using the controlling parameters? So that's my question. I will put you guys to breakout rooms, okay, and we'll give you, let me see, it's 9:20 now. So probably about 3 minutes so we can finish on time, all right? Oh, let me recreate. Okay, so if you are not clear with this question, please let me know.
If you just calculate the SME, then that's more beneficial than trying each and every one.
Yeah, that's a good answer. What else? What do you think? Any other thoughts? I think Carly was right, because the SME kind of considered all those parameters inside that equation, and they cancel something out. And more importantly is that this is very specific to a material. For example, when we talk about how much SME the starch has received, basically that's very specific for the starch. So a food, how much it cooked, it's directly linked to how much energy it's directly there absorbed, right? So that's the one of the parameter that is describing um, the, the 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 thermal process or the mechanical process the material has gone through inside the box, right? That it, although it's black box, but we can kind of see how much energy they have received. So that's a direct way that we can link it to the final product properties. So good job, guys. All right, so I think that's one of the key part I was hoping that you guys can get after the class, which is great. All right, so brief summary. So we briefly compared the two types of extruder mostly covered in our last class, okay? And then we talk about all the chemical reactions, for example, glass transition, we didn't cover glass transition, but you see the product melted inside that extruder, right? And for chemical side, there's a glass gelatinization, the starch gelatinization, the protein denaturation, the formation of disulfide bond that forms that texture, right? And for the changes food products, you can see that they sometimes get a little bit more tender or more chewiness. And for puffed snacks, it's gaining a little bit more crispiness, right? And also there's water removal, cost expansion, and we also discuss about what is the SME and how to calculate it, and especially how to control the processing conditions. For example, barrels, the screw speed, the feed rate, moisture content to kind of adjust the product properties, right? So I think that's all we have covered in the extrusion. So hopefully on the Friday's lab, you have a better idea to understand how the system works. And also when you see those numbers, you'll know what that means and how that can be correlated to our food product. All right. So I think that's all for this class, and I'll see you on this Thursday, okay?
Thank you.